The topic itself is something that I've been attached to for many years, and I find out that there are a number of people I have found out many years ago, that there are a number of people in the high-speed community in particular that are connected with smear cameras and street cameras and velocity recorders and so on, but they practice what you might call an art that is not very well known. Talking sometimes about weapons and so on. Weaponry, as we know it today, wouldn't be what it is if it weren't for streak cameras. I don't think that's an exaggeration. So, what are these things? Well, by way of a brief review, we'll talk about or spend a little time discussing kind of the basics of where these cameras come from and what they're related to. And I mentioned these in the past already, but a little review is, I don't think, not a bad thing. So, street cameras are related to focal plane shutters. You say, well, okay, what's so special about focal plane shutters? And you already should know what is so special. But anyway, they operate in quite a different manner than leaf shutters, on the right, in terms of exposing an image, either on a digital or an electronic sensor or on a piece of film. It doesn't matter. They do it the same way. So the leaf shutter exposes the whole sensor at the same time, everywhere. So the corners, the middle, the sides, the tops, the bottoms, all see light at the same time. They all see light increase gradually as the diaphragm opens up, or as the shutter opens up, and then light decreases everywhere as the shutter closes down. It's a very important, it's an important thing if you're ever going to make measurements from the photograph, that you know what kind of shutter was used. I should mention, in addition to these two, there's also the electronic gated shutter, which does the same thing as the leaf shutter, except for the fact that it starts to capture much faster and cuts off much faster than the leaf shutter does. So you could think about it as a leaf shutter that opens up instantaneously and closes down instantaneously with the exposure time in between those two events. Anyway, the focal plane shutter, as we've discussed, is a slot that moves across the image plane. And at one point here on the left it's at the top, on the other one it's at the bottom. And the image is exposed sequentially from top to bottom. I like to call these slit scan photographs. Now, slit scan is a term that has permeated the popular photography language in, I think, not quite proper ways or correct ways. But I think if you take an image and you scan it with a slit, you're doing slit scan photography. And so what's the relationship of these two kinds of shutters with the digital world? Well, there are two, the focal plane shutters, and I think I demonstrated the rolling shutter effect with an iPhone, I think, are rolling shutters, while the leaf or diaphragm shutters are global shutter. For the sake of background information. And there are various kinds of distortions that become apparent when you photograph moving images. The objects don't have to be moving, but their image has to be moving on the sensor with respect to the scanning action of the shutter or the CMOS sensor, typically that's what it would be, as it scans the image plane. So the leaf shutter, all it will show you if you photograph, or the global shutter, okay, would simply show a circle and a square with blur, okay, on the sides, if they are in motion. That's about it. Every one of these, looks the same. On the other hand, if you have a focal plane shutter, a slit scan system, where the slit is moving downward, okay, like this one here. In that case, you can, well, let's see, it could move downward, it could move from one side to the other, from that side or upside, whichever way it moves. And there are the illustrations. So in this case, the slit is moving in the opposite direction that the images are moving. So now you get a compression. And why do you get compression? Because it takes that slot less time to go across that image than it does if the image had been standing still, which is here. If it moves along with the image of the subject, in that case, assuming that it passes it, okay, because it's also possible that you see it go through the viewfinder and nothing shows up on your frame. Why? Well, the shutter never caught up to it, even though it was in the frame at some point. So that's this situation over here. This is traveling faster than this, so it'll catch up to it, and that will result in a stretching out. And the reason for that is now it takes that slot longer time to pass over that square and circle the square than if it had been standing still, which is the case over here. And then you get leaning to the left or to the right if the motion is at right angles. Basic focal plane shutter distortion, or rolling shutter distortion if you want to do it in digital terms. So and this is a typical result of what you might expect if you scan an image that is moving with a focal plane shutter or a rolling shutter. In the case of electronic cameras, you don't have much control over how fast the scan takes place, but with something like a better light camera back that has a scanning array that you can move, you could easily make pictures like this, where this is done with her essentially holding his head, okay, at some point, but after the scanning slot has gotten to his neck, she lets go, hopefully, and as this slot is coming downward, he's also sitting down, and eventually sits down, stands still, and that's the end of the picture.
How long did it take around?
Maybe 20 seconds, 20, 30 seconds. Yeah, it was done with one of these boxes here. It has a slot in it, and the camera sits in the back, and you look out through the box and you see the moving slot. So you simulate a focal plane shutter, but instead of having it inside the camera, you have it outside. And you could just as easily have a digital camera in the back as an analog camera. It doesn't matter. In this case, the couple changed positions over time. When the scanning slot got to here, they moved around, and then they came back to the original position. The interesting thing is that it included a dog in the picture, who's not distorted. That means that he must have been standing still for the time that it took that slot to pass by it. But anyway, this is focal plane shutter distortion. Now what we're going to do is to take a look at a variation on a focal plane shutter exposure effect, and we'll do it by, I guess, imagining or setting up in our mind, conceptualizing a situation where we have a camera in which there is I guess I didn't put the digital equivalent to this, but let me do it this way. In which there is an open slot, focal plane shutter slot. Okay. But instead of it moving anywhere, it just sits there. And behind it, we have recording material. Film. If this were a digital camera, and now that I think of it, I think I made a slide or whatever that kind of gave an analog of what a digital system would be if it weren't film, okay, in the back. And I think that's coming up, hopefully. So anyway, there's film that is able to move past here, and there is an opening in front of that moving film. I like to think about film as computer memory. It is very good memory. It is very cheap too. But if you bear with me for just a bit, we're going to devote some time to film, and we're going to ignore everything else. Okay, there is got to be a lens to make an image of anything. There's going to be, if you're going to have a photosensitive material behind the slot, you're going to have some kind of means of excluding ambient light, so there's a light-tight box, there's a lens. Now, there is no shutter, though. Okay. This just sits there. So supposing that you have made this box, it's got a lens, it's got a means for moving film past that open slot, and then you put an image of anything, of something, across that, and it would be this, maybe this white bar. Could be a lamp, could be a piece of board which you painted white. So there it is. Now notice that most of this part of this subject and that one is falling on a mask, so it has no influence whatsoever on whatever is recording the medium. But suppose you have this camera and this light, supposing it's a fluorescent tube, just sits there, and you've turned it on. Make sure you turn it on, so there is an image there. And from the time that you that you've loaded the camera with film, and you start to move the film through the camera, and eventually you run out of film, this condition, okay, is maintained throughout all that time. So if I were to ask you what the resulting image would look like, would anybody be able to tell me what it looked like? A long white streak. Okay? So, yeah, it would extend all the way from the very beginning of the record until the very end of the record. It's not very useful as it is, right? Because all you know is that there was something there that caused some effect on the photosensitive material. But our objective is to make it useful. So suppose now that instead of keeping that lamp turned on all the time, you start recording with the lamp turned off. So there is this memory going by that slot. And the slot, you can think about it as a digital array, as a linear array. You'll see I put it later on. But anyway, there is that lamp sitting over there. It's turned off. You're starting to make a record. You're looking at nothing. And eventually, you turn the lamp on. Then you turn it off. And you keep recording of darkness. And then you turn it off. And now if I ask you, what would the record look like? What would the answer be? Blurt it out. Yeah, dots of light. Streaks of light. How about it would be a record pretty similar to the previous one, except it would not extend all the way to the edges. It would be a shorter signal, right? It might be something like that. It says, I turn the lamp on over here, and I turn it off over here. So is this useful? Well, it's useful in a number of ways. It could be useful in a relative way, because you could say, well, the length of this stands for the length of time that the lamp was turned on for. But you don't know how long the lamp was turned on for. You just know, well, it was turned on for this length of time. So how do you find out how long the lamp was turned on for?
Reality, I suppose.
You would be able to tell that if you knew how fast the recording medium was moving. The film was, if it was a film camera, right? How fast it was moving. So supposing that you were moving the film at an inch a second, and then you measure this, and it turns out to be it's 2 inches long. From that, you can deduce that the lamp is turned on for how long? 2 seconds. Pretty simple. Now, you could determine that the lamp was turned on for 2 seconds with a stopwatch too, couldn't you? Yep, you could do it. But suppose this is only on for 1/100th of a second. How much good would a stopwatch do you? Not much. And what if it's on only for a femtosecond or a picosecond, whatever they are? Extremely short duration. Stopwatch is no good. So you need to think about some other means for analyzing duration. Just simple timing. Okay. And in fact, with a system like this, you could put 4 or 5 lamps along the length of that slot, or along the length of a linear array, and turn them on at different times. Or maybe you turned them on at the same time, or you think that they're turned on at the same time. You'd be able to tell whether they all were synchronized or how far off each other was from the other. In fact, cameras like this are used just down the street over here at the U of R to do exactly that. Because over there they have to hit some little target with 24 humongous lasers. Okay. And they all have to happen at the same time, so that all the energy of the lasers goes into that pellet at the same time, because if it's at a different time, then you don't get the kind of energy that they're interested in, because they're trying to do some fusion experiments. And energy levels are very important. So they can time, or they can visually see whether the lasers hit the target all at the same time. All with this system. Operating a little faster, I agree, but same thing. Now supposing instead of having the images stay on that slot, you do something else. So that the tube moves from here to here to here, continuously. What would the final record look like? Okay. Very nice, a diagonal line. Okay. Now the slope of this line, the angle that it makes compared to the horizontal, is going to be an indication of what? How fast it's moving. Again, over here, the faster it moves, okay, from here to here, the steeper the angle is going to be, right? In fact, if this could move from here to here in no time at all, what would this angle be? 90 degrees, right? And if this is not moving at all, it just sits there, then the angle is what? 0. That's the first condition, right? So now it's become even more useful. It's become a system where we can determine how fast things are moving, not only how long they last, or if they're simultaneous or not. In this case, supposing that the film again is moving at 1 inch a second. In that case, we could determine how fast the image of this object was moving. The image, not the subject yet. If we knew how wide 35 millimeter film was. How wide is 35 millimeter film? Anybody know? Yeah, this is one of those. Did I ask you this before? No? Anybody remember me asking you this before? See, I've asked this question from audiences for the last 20 years. So I don't know who I've asked this from before, and I apologize for that. But it's a great question. Well, it's a funny question. 35 millimeter film is 35 millimeters wide. See, it's one of those that, duh, why didn't I think of that? But it's amazing that you could ask seasoned professionals, how wide is 35 millimeter film? Of course, nobody uses film anymore, but that's kind of besides the point. And I bet you, probably 90% of the time, you'll win. And if you're in a bar and you're betting for a beer, that's pretty good. So, we know that the distance from here to here is 35 millimeters. Now all we need to know is how much time elapsed between the time that the tube was here and the time that it was at the top. Okay? And we measure this, and it's 1 inch long. And the film is moving 1 inch a second. Okay, so from here to here, it's 1 inch. Film moved, or the image moved 35 millimeters, so the image was moving at what rate? About 35 millimeters per second, right? 1 second, 35 millimeters. The system has become a velocity recorder. And if the image accelerates or decelerates, instead of getting a straight line like this, what are we going to get? curved lines. Okay. So the image can curve like this, or it can curve like that. Now, if you have a record that looks like this, what can you tell about the performance or the relationship of the image? Well, the performance of the image. What was it doing? It was speeding up, right, because it's becoming steeper and steeper, right? And over here, you can tell it's slowing down, right? So, wow, you know, you've gone from this very simple system, you know, a slot, moving memory behind it, and now you can make some measurements. You do need to know how fast the record is being made, okay? But typically, that is a piece of information that you have. You set that in a camera system. So now we'll take a look at a different aspect of a subject. Okay, it could be sitting over here, but the image, instead of just standing still, it's vibrating. It could be a tuning fork. It could be a relay operation. It doesn't matter. It could be a bunch of things. So what do you think the record is going to look like this time? Yeah. If I can see fingers going like this, yeah, sure. I'll buy that. You get a wavy line. Again, you don't know what it is that you photograph by looking at the photograph. Okay? But this is powerful stuff in high-speed photography if you're going to make a measurement of the rate of vibration of some subject. It is... you know, if you have something, again, that moves up and down rather slowly, you don't have a problem, you know, with the stopwatch measuring, well, how long does it take? But if it's doing it quickly, well, now you got a problem. And on top of that, if what you have is a stopwatch to measure anything, anybody who you communicate with later has to take your word for the fact that things worked in a particular way, or that you're giving accurate timing information. You can publish words, but they're not really related to the actual event that happened. But a streak record is. This, if you publish it and you put a time base here saying an inch is 1 second, anybody with an ounce of intelligence will be able to interpret that photograph as, oh yeah. Of course, he's got to be telling me, yeah, this is an inch is 1 second. I got to buy that. But if that's true, in that case, I can work the rest of it out. And so you can print this in a publication, in an article, a scientific paper or a popular paper. It doesn't matter. So street cameras are powerful things. They are related to, historically, to these things. Anybody know what it is? I think this one is sitting over there. They're called strip chart recorders. And they have paper, in this case, that can be moved from a supply spool to take-up spool at some speed. You can select the speed. Someplace there's a controller. Maybe it's on the side. I don't know. And up here there's a pen, okay, that can be moved across the paper as the paper moves forward. So it leaves a trace. And that trace is associated typically with voltage that you gather from someplace or another. But lie detectors, electrocardiograms, they use strip chart recorders. They're just a pen, maybe 2 or 3 pens. But the neat thing about the optical street camera is that you can, where pens can't, they can't occupy the same place or cross over. I mean, sometimes they're made so that the pens are at different distances from the carriages, okay? But that's kind of a pain. In the case of a streak record, an optical streak record, you can have light signals that move up and down that slot. And you can track multiple events. But anyway, this is a popular device which is used in many situations to to monitor the performance of subjects. So how can you do something like this if you're trying to simplify or make a very basic streak camera? Well, starting with the film approach, I'm missing a slide. I don't know where it went. Which essentially said that anything, let's see, I think I can go back here. I thought I could go back. Which, maybe I'll find it later. Anything over here in the film, or anything that's coming, would be, I would call, unused computer memory, because it's not been exposed. Anything on this side is a digital information which has been stored in memory. Essentially, this is used, this is unused. And this is where the signal comes in. That's where a linear array would be placed. A linear array is nothing more than a bunch of pixels, one on top of the other. Just one column. Sometimes three for RGB, but it's easiest to think about it as just one column of pixels. And you say, well, if you have one column of pixels, how do you, what happens with the moving film and stuff? Well, those pixels are read out by hardware and software at a particular rate, and the rate at which the information on those on that array is read out can be translated to elapsed time. So the rate at which you store memory this way is what the digital versions of these cameras do. And I think we'll see a couple of examples of them later. So, but how can you, in a simple manner, in an analog photography manner, simulate or actually make a streak camera? Well, you can do it this way. You can take a camera, you can take its focal plane and put a couple of masks in and leave a slot in the middle. Typically in the middle, or it could be anywhere, okay, but you need some kind of an opening. Now you don't actually have to put a mask in there, but then you'd have a really big slit, and typically that would not be very useful. So now you have half of a streak camera made. Okay? A slot in the back. What else do you need? You need to have a means for moving the film. Well, in a camera like this, the film is moved every time you advance it with that thumb lever, or with a motor drive, or whatever it is, but it goes forward. But and it does so in pieces. So some comes up, it goes up to here, and it stands still. Okay, and then you get another one, and it stands still again. Well, it's an intermittent motion. That's not too useful. You'd like continuous motion. Well, you can do that if you before you do any photography. You put a lens cap on, and then you advance all the film from this side to this side. Okay, so now all your memory is here, unused. And then, to use it, you lock the shutter of the camera open, and you rewind the film. So now you have a means for continuously moving the film from right to left. And that gives you the time base, which is then useful in a streak application. So, since you're doing it with the rewind knob, which is kind of puny, it might be interesting to enlarge the lever of the rewind mechanism by making some kind of a contraption, like this. In this case, it's a film can, plastic film can, cut a hole in the bottom. You slip it over force it over the rewind knob, and you put in a pencil through a couple holes. So now the lever, instead of being this big, it's quite huge. And it's much easier to turn that at a constant rate than it is to turn that little one. One fact about this is through extensive research in the Imaging and Photographic Technology Department, some bright students figured out that the best levers are made by number 2 pencils. No laughs. Damn. My timing is off, I guess. So anyway, the precision of any kind of application depends on how smoothly you can move that film. And there's various attempts that have been made to make that film move at an even speed. For example, by using a motor drive to drive the rewind knob. So this thing turns, whatever, and that turns the rewind knob. And say, well, that's going to be a more even rate of motion for the film than if you did it by hand. Yeah, true. Here's another less complex bracket. It does the same thing. I forgot what I was going to say about this. Oh, but because now the rewind rate is constant, okay, maybe it goes around once a second or so, or once every 1/10 of a second. It doesn't matter. There is still a change in film speed involved. You'd like that speed to be constant, okay, from beginning to end. But it won't be, because in a camera like this, you start out with a spool, an empty spool over here, right? And then over time, you build up diameter. And the more diameter you build up, the more film that's going to go through the camera per revolution of the rewind knob. So the speed is going to be increasing.
Do you still have these on the page?
Nope. Nobody's using them, so, I mean, I checked with them, and
If we plan on doing this, how would we get this? Would we have to ask them? Do they still have one?
I have two of them. You can ask me and I'll give it to you. Yeah, it's just that over there that we're taking up space.
Yeah.
So, on the other hand, if you want consistent speed, okay, in that case you need to drive the film in the opposite direction. And this little $5 prize camera does it. So over here, there is this sprocket, and this motor drive came out of the garbage can someplace, is connected directly to the sprockets. So when the sprocket drive turns, it turns so many sprockets every second, and that is consistent from the very beginning of the roll until you're out of film. So in this case, the speed will be uniform. However, you might introduce some small variations because the film doesn't want to always fit onto the sprockets as smoothly as you'd like. But anyway, in general, this will give you a consistent speed from one end to the other, if that's of any importance. Now, what can you do with a camera like this or like the other ones? Well, you could make, remember the velocity graphic a little earlier? Well, in this case, we would be looking at a rocket taking off. And we're not going to do this with a streak record here, but we're going to do a different application for a rocket taking off. And it'll be happening here, and this was done here, and the rocket goes into that hole. So anyway, this is a trace of the engine exhaust as the rocket is taking off. And down here there are timing lights provided by a flashing light every 1/10 of a second. Okay? Well, every 20th of a second, right. So this just tells you from here to here is a 1/10, etc. So 1/10ths are marked off, 1/2 of 1/10ths or 20ths. And you see the rocket sitting over here. Now the engine has already ignited. There's already light coming out, but the rocket is still sitting on the pad. And it's still sitting on the pad. You can tell it because the slope of this is flat. And eventually, though, it starts to lift off. This is just like what you call, the real rockets. If you watch the shuttle take off, it does the same thing. It accelerates. Okay? At the beginning, it moves rather slowly, and then boom, it goes. So this does the same thing. You can tell that the curve is it's accelerating quite fast over here, and eventually it smashes into the ceiling if it doesn't hit the hole. So if you were so inclined, okay, you could figure out how fast the rocket is moving at any point. This curve has a mathematical expression. I would recommend asking a math person to do that. Say, well, I have this curve over here. Why don't you give me a hand? Now, the one thing which is not in the photograph is these lines. And they were added after the fact, knowing that the rocket was a foot tall. Okay, so you say, well, that's a foot. You put add a little strips of paper on a print, saying, well, these are a foot apart. You could have done the same thing by putting lights in here. Before the rocket even took off, you could put little lights a foot apart and string them up. But they would have described streaks that go all the way through the curve, right? So because they don't go through the curve, you can tell, well, they were not there. They were added after the fact. So, but this is a perfect example of a situation where you have a rocket which is doing something, and you'd like to find out something about the speed at which it's moving at any given time. And you could do it, rockets like this, you could do with the simplified version of a street camera that I mentioned earlier, or we saw earlier. You say, well, it's all well and good, you're talking digital, you're talking analog and film and stuff, but what about digital? Well, cameras that do this in the digital realm, electronic realm, are quite expensive. And so I've never been able to buy one. And nobody ever offered to give me one either. So at one point, I ran across a device, this one, which was a hand scanner. And this is something that was more prevalent before flatbed scanners became popular. So now you can't get hand scanners typically anywhere. So it consists of a little wand like this. You hold it in one hand and you roll it over whatever it is that you want it to scan or copy or whatever. And you'd be able to do something which was like 4 inches wide by maybe 10 inches long. So although it would not cover an 8.5 by 11 sheet of paper, you could do it in multiple swaths, right? 1, 2. And then the software, the people who put this together are pretty smart people. They live in Taiwan. Figured out a way of what we're doing today, stitching images together. And so they would look for areas that were the same in both images, and they join them together. Smart stuff. Got to give them a lot of credit. But it all came bundled with this device. The intent is for you to copy things. So I said, you know what? I bet you that inside of here, they have a linear array. And what they're doing is they're moving the image of whatever it is that they're copying over that linear array and gathering information off of that array and putting it into memory and so on, and then stitching them together. At the time, these were being dumped on the surplus market. And I paid a whopping $25 for it. I figured, $25 is like going to the movies a couple times. So I can afford that, even if it didn't perform the way I thought that it would. But anyway, I did get it, and sure enough, as after you open up the guts of this thing, down in there, bottom, someplace, there was this thing. A linear array. Now, there's a bunch of pixels from here all the way to there. This may be an inch long in this one. Okay. So, hey, you know what? This is pretty cool. Because what I'm going to do, instead of making the scanner put an image using its own optics, okay, what I can do is put this in the back of a regular camera and then make pictures with it. Of course, once you take this out of the hardware here, you have to connect it again. It takes a little soldering, a few wires need to be soldered together, identified, and so on. But it turned out that it did work, and so here's the array being attached to the back of the camera. So notice this, whatever, anybody know what this plug is called? It's the same one that's on the computer here. It's a 12-pin thing. Anyway, so here it is, and there's another one like this on the body of the scanner, and I built a cable to go between them. All of it is kind of kludged together with resin glue, and so now it's going to have another piece attached to it on the other side, and then it's already in the back of the camera. So here's the camera back, okay, and it's in the back of the camera, and this is going to be made so it can slide back and forth, because there are applications for that too. Well, the focal plane shutter pictures can be made that way. So here's a view from the front of the throat of the camera. And here's the hardware part of it. So originally, this wheel here that has little slots in it would turn as you roll this. There was a roller here that I took out. As the roller turned around, this chopper wheel would also turn. It would interrupt a light beam or an infrared beam between a receptor and a source. And the rate at which it was interrupted was a function of how fast you were moving this. And the software knew that it only had the capability of scanning that linear array at a certain rate. And if you're moving too fast, it said, hey, slow down because I'm missing information. So there was a built-in safety information that popped up on the computer that said, you're going too fast. Going slow was not a problem. But because this wasn't going to be moving anywhere, I wasn't going to roll it or anything anymore, I had to substitute something or make that chopper wheel turn anyway, so that the software in here would think, if software could think, that it was rolling. So I took this gearhead motor, put it over in here. This turns, that turns the chopper wheel, and everybody's happy. So here's the whole contraption put together. The array in the back, the cable that joins them, and you push a button, and this thing starts recording the array, and you make streak pictures with it. So what kind of pictures can you make with it? Well, you can get quite creative. Probably not like me, but here's a couple of them. Now these have been turned on their side, but they're the tops for these dry erase markers on a turntable. And some of them are close to the center, and some are close to the edge. And as they're rotating on the turntable, the linear array, which is oriented horizontally, is looking at what's being projected onto them. And the tops move across the field of view. So one of these, I think I'm giving you, in this photograph right here, one of the tops is close to the center of rotation of the turntable. Which one is it? The red one. It's actually not exactly centered, because it is wobbling a little. If it were exactly in the center, you'd get a nice straight line, right? You'd still see a corkscrew pattern of the details on the surface of that, but it would be a straight line. And the further away you go, this one, whatever that was, black.
So you're looking down on that turntable? I don't understand.
Sideways. The turntable is turntable. Okay. Yeah, let's see. So there it is. So it's rotating. I'll do it now. Here we go. 3 tops. Okay. So we put a top here. Put a top here, and we put a top here. Okay? And you're looking at it as a line over here, right? And storing the information up or down, it doesn't matter, whichever way you want it. So here goes. Now they're all in line, right? And that would be, well, I don't know what that would be Well, obviously what's happening over here is that they're never in line like this in this layout, right? Maybe like that. They're on opposite sides. Okay, so anyway, here goes. And so, well, that one is a little closer. So that's how it goes. Okay. It would have been probably easier to visualize this if I hadn't turned them 90 degrees. But it was more interesting this way. See, now you're talking about art. And the bottom one, I don't know, is all screwed up. The color is all screwed up. And then once you have things like this, there are a number of people that have done similar things with flowers and stuff like that. Very neat things. I'm not that creative. So, but once you have something like this, you get seduced by Photoshop. And you say, oh, okay, you know, I'll cut it in half and flip it, and then you have to do them side by side, whatever. So now we'll take a look at some applications. They're make-believe applications, so to speak, but applications nevertheless. So here we're going to take a look at the operation of a focal plane shutter. Okay. We did this with the Phantom, but in this case, the linear array is in the back of the camera over here, or wherever it is. It must be over here someplace. Probably over here. It doesn't matter. It's in the back here, and it's lined up vertically, going across the throat of the camera. And the camera is going to be activated for 1 second, half second, quarter second, and so on, as this very same digital street camera operates. So it was made with this simple hand scanner system. And here's the result. So the shutter is open, and the timing lights, so there's a stroboscope that's giving you timing at 1 every 1/4 of a second, so 4 a second. So you can tell that anything which is 4 of these blips long lasts a second. Anything which is longer than that lasts longer than 1 second. So this gives you timing information, but the actual performance of the shutter now is that long. It's that. It's that. And you can just qualitatively see that as you go along, as you're changing the shutter speed by a factor of 2 or a half, the length of those traces decreases by half too, which is exactly what you want, right? And if you were interested in precision, well, you could go to the trouble of measuring it more accurately than a simple visual exam. What about something else? Remember I said something about the lasers hitting the target at the same time? Well, I don't have lasers, but I do have a couple of lamps. Notice the camera now is returned, so the array is looking at these 2 lamps, like this. And so you're going to try to determine, or this is going to try to show, whether the 2 lamps are turned on at the same time, and if they're turned off at the same time. And there you go. So again, the important thing to remember in street cameras is that this dimension, or one dimension, is the time dimension. You can tell, well, I don't know if you could tell that they turned on at the same time, but roughly maybe. But this one was turned off after this one was, right? And in this case, well, this one lasted less time than that one did. So you can get some quantitative information. You don't have to just guess at it. And in fact, and this again can be published. Okay? You can print it and say, hey, look, this is the performance. You don't have to take my word for it. This is just 2 lamps, and at the laser lab, 24 lasers. Same kind of image. What about if you wanted to determine the wicking action of a piece of blotting paper? Okay, so you have some dye in here, the blotting paper, and this has a mark that I think it's at 5 centimeters, and there's some ink in here. camera now is lined up, the linear array is lined up this way. And looking at that every so often and accumulating that as an image. And I think the scientific term or the medical term for something like this is, anybody know it? Chromatography, where you do exactly the same thing, and then the composition of the material that you're drawing up shows up as different colors extend throughout the length of this piece of paper, so you can tell what it's made of. Yeah, pretty smart. But if you wanted to again publish the performance of or what happens as this material is being wicked up, well, you're kind of sunk. But a street camera can look at that one line, and then I think this is the situation. Okay, there's a scale, so you could actually eventually now determine how fast that die is moving up, and it looks like this. Okay, again, you got time. Somehow or another, you put a couple of interruptions here. I think that's what these were. You just a card covering up the lens and uncovering it. That puts a black line down. You wait a second, you put another one. So now you have a timing mark. Anything that's that size over here is 1 second. So you could say, for this to travel from the beginning, at the beginning the die goes real fast, right? And then it kind of slows down. Say, well, if this is 1 second, you can say, well, 1, 2, 3. Well, let's say in 4 seconds, it has moved 5 centimeters. So it's moving a fourth of a centimeter per second, right? Oh, 5 centimeters in 4 seconds. Well, how fast is it moving? A fourth of a fifth, 1.25 centimeters per second. Right. Okay, so what else can you do with this? Well, you could examine, for example, you could determine the stitching rate of a sewing machine if you had to. And again, you could publish this. That's the neat thing about these. These are time records that can be printed. You don't have to take somebody's word for it. So you put this linear array, you're looking at the needle going up and down, and you get some kind of a record at the end. It might look like this. And when the sewing machine, some things are going down, other parts are going up. And they will be visible over here too. And some things are standing still. Well, like whatever this is. It's not moving anywhere. Okay, suppose we expand this a little bit further. And we put a weight on a spring. Spring stands here, there's a spring in here, there's a weight on it, and you go boing, and then it goes boing, boing, boing. Right? That's what's going to happen, right? So you aim the array along that weight. And you get a record that looks like so. Here the thing has been pulled down and then released. When it's pulled down, it's standing still, then released. So, oh, it goes up, and it goes up that far, and then comes down again. Again, if you had to determine what the rate at which it's moving up and down is, you'd be hard-pressed trying to do it by hand. This gives you a printable, publishable record, indisputable, of the motion of that weight according to the spring. And obviously this eventually would taper out. Okay? And you could study that too. Well, how long did it take for this mass to stop moving up and down? Yeah, we'll do something a little more complicated. In a physics experiment, there are inclined ramps, right? And things roll down inclined ramps. There's a ping pong ball going to roll down an aluminum track. Okay, so here's the setup. There's the inclined ramp. Here's the camera. This time, the array is lined up along the direction in which the ball is moving. So it has a slight angle just the same as the track does. You start recording, you let the ball go, and you get a record that eventually might look like this. Without these lines in. What you get is this. So the ball is standing still over here, You let it go, it accelerates, it hits the bottom, it bounces up, and then bounces down again, and so on. It's like falling off a log over here. You say, well, how long did it take it to go from the top to the bottom? Well, if you put timing marks in again, what, half a second for each one of these. Half a second, that's 1 second. Almost 2 seconds, right? But you could get more precise if you measure it more precisely. You might not think it's a lot, but in a research situation, high-speed situation, this is worth its weight in gold. It's data about the performance of a high-speed subject. Now what happens if you take 2 ping pong balls and let them down? Well, the trace might look like this. So this is the earlier time. Let the ball go, hits, bounces, and tapers out and settles down. And then at this time, you let the second one go. It comes down and hits the first one, which is already standing still, and they both bounce up. So you transfer some of that energy into the first ball. So they both bounce up and then they both bounce down. So you have to get used to, I'm sure, to interpreting these. But again, if you had to do this just by looking at it, it would be pretty hard to do. Say, well, it took it 1.5 seconds to do it. No. This does it for you automatically. Here's kind of another simplified example. A martini glass filled with what? What's your favorite drink? Vodka something? A vodka martini. Okay. So anyway, here it's sitting, and you look at the surface of this liquor, and then you say, well, what I'm going to do is just touch it and cause ripples to happen. And now I want to find out how long it takes for the ripples to disappear, for the surface to become smooth again. Because I think that vodka settles down faster than gin. It's whatever, okay? So how do you determine how long the ripples stay on there for? Well, you take the linear array, you look at the surface, okay? And you might get a picture that looks like so. You can see the ripples over there. This is where it started, and kind of this maybe is where it ended. And this is a 5-second time interval caused again by putting an obstruction in front of the camera lens, and then 5 seconds later another one. So it kind of tells you this. Well, maybe it's a little bit longer than 5 seconds, okay? But you can give a quantitative answer to the question: how long does it take for the ripples to settle down? And again, the powerful thing about these, they're publishable. They're illustrations that go along with an article. You say, oh, okay, well, I've seen the simplified versions. Are there more sophisticated versions that if I were infinitely rich, I could buy? It's one of the reasons that I don't have one. Yeah, and I'll show you a couple of them. This is a company, Hadlin DRS, makes a digital street camera. This very same thing that you've just seen for $25, except that this camera can look at those lines in a millionth of a second increments. So the whole line in a millionth, the next one a millionth later, next one. So the time resolution is much better. With film cameras, the time resolution is given by how fast you can move the film and how fine the slit is. In these, time resolution is given by what the readout rate is for the linear array. And these can do it pretty quick. Price tag? Anybody want to guess? 100,000. So here's a Photosonics company. Also has street cameras. What are they? Optronics or something? Price tag, same region. So these are probably in the $100,000 to $250,000 range. Depends on how fast you want them to go. Corden is one of the significant high-speed companies in the world but for sure in the U.S. So they've been providing high-speed, you might say high-speed solutions to the government for years, from the 1950s. So these cameras have time resolutions that for a bit of an image may be I don't know quite exactly how to quantify it, but in terms of they have a time resolution that is where you can make measurements of time that are as small as those that I mentioned earlier, a femtosecond or a picosecond, which is a thousandth of a millionth of a second, or a thousandth of a millionth of a million, thousandth of a thousandth of a millionth of a second, femtosecond. You just keep adding zeros. You say, well, why would anybody need anything like that? Well, there are not too many people that need something like that. But the people who do nuclear work, unfortunately, they do. So they're very specialized, price is way up there, but they do nothing different than that little hand scanner thing. And just kind of as a parting illustration, flatbed scanners are also, in a way, street cameras. Okay, so if you have a ruler that you make interact with the moving light wand, in that case you get a record in which there's time introduced. The time is introduced by the fact that the wand is moving at a particular rate, and the displacement of the ruler along that wand gives you space information, dimension. And so you could determine how fast that is moving if you know what this distance is. And you do know it because you know how wide the flatbed scanner is, right? So, street cameras, a well-kept secret. All right. Well, we're going to take a little break now, and we'll continue with a little description of what it is that we're going to do on Wednesday. All right, so take a break, and we'll go on.